A debugger is how you get a view into a system that's too complicated to understand. I mean, anybody that thinks just read the code and think about it, that's an insane statement.
This was John Carmack, a legendary programmer and engineer, best known for building 3D games engines like Doom and Quake. But what is he even talking about? This is Lex, and he has a bug in his app. Lex was looking for a while, but he can't spot the bug. Doesn't matter how many times he tries. His teammate, Carl, has a perfect suggestion. Just print to see where the app goes. So Lex adds a print, but it doesn't help much. So he adds another one. This isn't helpful. Lex is confused.
Adding log statements, recompiling, and rerunning it is an incredibly inefficient way of doing it.
Deep down inside, Lex knows there's a better way. There must be.
It's amazing what you can do with sometimes much, much better tools. Sometimes you could fix things even before you did one compile cycle. You could say, well, I'm just going to change this right here, and yep, that did the job.
So today, we're going to talk about debugging, a skill that while many users have ignored in the past, with the growth in AI-generated code is slowly becoming essential for those who want to survive the AI flood. But we're not going to just talk about any debugger. We'll be using an open source implementation within Neovim. I'm a LazyVim user. There's a video I made about it, but you don't have to be. NVim DApp, the debug adapter protocol from Neovim, is available to everyone, constantly updating and has improved a lot recently. However, I am going to use a bunch of plugins for this setup. One of them is NVim DApp UI to set, well, the user interface for the debugging process. Now, with LazyVim, these are installed as a lazy extra and everything is done for the user. You have the entire list of installed plugins, both in the lazy docs and on my .files. They're grouped under DApp and DApp core. With all that out of the way, let's install these extras by adding dapp.core and have lazy take care of the rest. And there's our shiny new key mappings for all things debug. Now, as for language-specific installations, LazyVim users are covered by the language packs, and non-lazy users can follow the docs. I'm using the Golang pack here, which comes with nvim dapp go. Similarly, Python devs can find nvim dapp python, and you've got other setups like the Java debug adapter and another one for TypeScript, JavaScript, and pretty much every other language. Let's jump straight in, shall we? The first thing to get familiar with when debugging is breakpoints. I'm sure most of you have heard of them or used them in other setups. In this instance, setting a breakpoint is done with leaderdb, D for debug and B for break. This means the next debug cycle, assuming other errors don't pop, will stop at this point. Let's see this in action on a larger screen to make room for everything that's about to come. And you've already got a small keycaster on the bottom right hand corner. Okay, let's go. Leader.du toggles the UI. We've got a bunch of splits here, also known as the debugger elements. This can be popped to a floating window, moved around. The layouts can be reconfigured later for those who like to customize. So let's run a debug cycle and see these fill out. I'll reset the breakpoint to line 32, where the Redis endpoint variable is being tested. Leaderdc for continue shows the debug options. We'll use the standard debug. The process runs, it hits the breakpoint, which is now marked with an arrow, and check out the surrounding UI elements. To the top left is our local variables and available scopes to the debugger. In this instance, showing that Redis endpoint is, in fact, an empty string, and it's kindly showing the variable type. The next pane is a list of current set breakpoints. The next element is threads and stack frames, and stick till the end to see how threads, which are especially hard to debug, play nice with the help of this section. Then there is your watch expressions, which are extremely useful, serving as an interactive prompt console for reading values and setting others. Here, an expression can be expanded, showing children, changing their contents, and more. I puts you in insert mode, and let's look for the Redis endpoint variable that comes up with an empty string. This becomes immensely powerful when looking at complicated logic and a lot of variables. This complicated logic can come from many places, and while it used to be a problem of enterprises and large teams, with AI stepping in hard, understanding large code bases and what they do, in my opinion, becomes one of the most critical skills for engineering going forward. Before running the process to see the debugger reacting, I want to share something that can go hand in hand with it: Augment Code. While traditional AI assistants might suggest generic fixes, Augment actually understands your entire codebase, making it perfect for debugging complex systems. Unlike Unlike other tools that focus on writing new code, Augment excels at helping you navigate and understand existing architecture. What makes Augment different is its speed and deep context engine. It responds almost instantly, even on massive code bases, and can answer complex questions about your entire system without you needing to tap a colleague on the shoulder. Imagine having a principal engineer available 24/7 who knows every line of your codebase. Teams like Webflow, Lemonade, and GoFundMe are now trusting Augment with their large code bases because it truly understands how their system works, not just how to complete a line of code. But wait, this one gets even better, and now it's personal. Augment is Vim first. There's a Neovim plugin, which you've seen me working with, and it's an absolute blast. While other platforms force you into VS Code, or worse, the browser, the team in Augment knows what real devs need. Just one look at their plugins domain tells you everything you need to know. Try Augment for free, no credit card required, just visit augmentcode.com to start debugging smarter, not harder. Now, let's go back to the debugging demonstration. Let's see how the system reacts in real time, adding a change in the Redis endpoint and another breakpoint on the Redis client creation. Running another debug process, the first breakpoint hits, we see the current watched Redis endpoint var is empty. Let's hit leader DC again, continuing to the next breakpoint. Since in between the points I've made a change, the value is now shown both inline and on the local span. Let's go deeper. While here, we try to look for the Redis client object that comes with a pointer. Hitting enter to expand lists the children of the object, which we can expand further and further. I hope the idea of having a debugger look into your code is starting to make a lot of sense. But watching variables is not even scratching the surface. With a debug session, we can make it step into a process. With leader DI, we go into the current point, taking us into the information of the current client in the new client method. Now, bear in mind, this isn't even my code. It's a Redis dependency brought in, yet the debugger goes in as much as we tell it. The function now shows every single passed argument, including its values. Leader DO will step out, back, the same stack, all the way up to our breakpoint. All of these are great, but without the ability to manipulate code while it's running, a debugging process isn't as powerful as it can be. Remember what John Carmack said?
Sometimes you could fix things even before you did one compile cycle. You could say, well, I'm just going to change this right here, and yep, that did the job.
So here we have an app that crashed going through a panic as expected, since Redis endpoint is Valkey instead of being localhost. And there's the bottom component with the log showing it. But what if, while debugging, we could change the behavior? So the session is now active, the breakpoint is waiting on line 3, and before moving forward, we explicitly change the value of the tested variable to localhost. Don't forget to save the document before letting the debugger proceed, and voila! Past the panic statement and onto the next change of the same variable. So far, so good. But what if you'd actually like to set a breakpoint that only stops if something happens? To demonstrate that, here's a simpler piece of code, a for loop running from 0 to 9. A naive debug flow will stop at the first iteration when I is 0. Note that it's not yet printed to the log below, as the line isn't executed yet. It will keep hitting the breakpoint again and again, slowly printing throughout. Now, instead of the usual DB, we hit leader D capital B, and a pop-up asks for a statement. We instruct it to only stop if I is 7. Running another session, and what do you know, everything's printed to the point where I is now 7 and the debugger is waiting for further instructions. This is a good point to stop and remind that LazyVim users can find the list of DApp key maps in a nice table listing every option seen on the menus, which are also available to users of WitchKey plugin. LazyVim users are enjoying WitchKey by default. The internal help docs for DApp widgets can help with customization like positioning of the scopes, the sidebar layout, even the cursor hover and preview settings. Last but not least, the one area of code I really can't do without proper debugging is multi-threading. I've added here a simple Go code that creates 3 workers in 3 different threads. Prints the thread index when it starts and a result when they're done. There's a wait group below, which is Go's way of telling the process to wait until the threads are done before finishing the work. I've also added 3 breakpoints. The first right after printing the start of work, another one if and when the thread is done, and the last one, which will actually hit first, the main thread's message about starting the workers. I didn't mention it before, but the UI, like any other pane in LazyVim, is set to be manipulated with the mouse as well, which comes in handy with DapUI. Let's start the process, and right off the bat we can see the main thread starting. Above we already see a wait group set, and we can move on to creating our workers by continuing to the next breakpoint. Right. Interesting things happening. First off, the code pane shows the wait group's contents in line as it's already set. Also note, in the threads component there's different threads showing up, each with its own stack, like the use of fmtprint, and all the way back to where it was sent from, in this instance starting at main.go line 26. Another cycle brings us to the creation of the next worker, also showing on the log on the bottom. It's always nice to represent threads using simple index numbers to show the randomness of their appearance and lifecycle. Jumping forward again, 3 workers active, 2, then 0, then 1, all of them showing as threads on the thread component, with their stack for the user to track and follow. Pushing yet another continuation to see 2 threads have already completed their work and printed it, while the third one is just about to do so, but we've stopped on the print line before it executes. This is a simple representation of the debugger's capabilities in the world of multithreading, which you can imagine becomes unbelievably helpful with complex systems, especially ones you're not very familiar with, maybe because they were written by someone or something else. Debugging and all is great, but if you're still battling installations of plugins and language packs to set up Neovim, here's your next watch, a from-scratch guide to getting LazyVim up and running in no time. Thank you for watching, and I'll see you on the next one.